Alright, so for my topic, I chose Faraday's law. Previously in class, we learned about how an electric current will produce a magnetic field. Faraday's law kind of teaches us the exact opposite, that a magnetic field can also produce an electric current. A basic explanation of that is this little drawing I have here. These two loops. So this loop on the left, you can imagine it has a switch that opens and closes, which will produce a current through this circuit. Here on the right, we just have a meter that reads a current that runs through it. No power source. But as we open and close this switch here on the left in this circuit, we see that a current also will pass through this circuit on the right for a brief moment, which is interesting. So a basic explanation of that is what's happening here is this current here on the left creates a magnetic field, and that magnetic field induces a current that will pass through this circuit. So a better explanation of that is can be seen in this equation that I have here on the left. So basically, the EMF that's produced by this circuit is equal to the number of terms multiplied by phi, this symbol right here, which represents the magnetic flux, divided by t in an inverse relationship with time, the change in time. So starting with magnetic flux, this phi right here, an explanation of that is kind of like, I like to compare it to rain that falls through a square or falls on the sidewalk. What's happening is the magnetic field, as it passes through a specific area, it creates a magnetic flux. So as rain falls through this square, based on the area, the size of the sidewalk or the size of the square, the more soaked the sidewalk will get. So if we imagine as we increase the density of the rain, so we add more raindrops in here, the greater the magnetic flux will be. As we increase the area of the sidewalk, if we pull the sides apart or pull our circuit wider, that will also increase our magnetic flux. And this cosine theta here on the right represents the angle between the normal line and the magnetic field. A lot of the time people will get confused and think that it is the angle between the area and the magnetic field, which is fine. You could use a different trigonometric function to solve for that, but it's more commonly used cosine and the angle between the normal and the magnetic field. So as we rotate our area, we'll have to account for that. Here on the right, we have a picture of if we imagine it's the same exact area, it's just at 90 degrees, exactly perpendicular with our magnetic field. So if we took the cosine of this angle right here, 90, we'd find that we have no magnetic flux. Cosine of 90 is 0, which is interesting. In the best situation, we'd have cosine of 0, which would give us 1, which would maximize our magnetic flux. So that's our phi, magnetic flux, and that has a direct relationship with our EMF. As we increase our magnetic flux with each of these or either of these variables, our EMF will also increase, which is similar to our N. If we increase our N, adding more turns in our circuit, so will our EMF increase. So this negative outside of the end represents Lenz's law, which is another concept behind Faraday's law. To demonstrate that and Faraday's law, we have a aluminum conductor right here, an aluminum pipe. We did this demonstration in class. We took a magnet and a steel ball or like a piece of metal, and we dropped. First, we dropped the metal through the pipe. We saw that it passed through without any problem. Passed through fine. Then we took the magnet. He had an eye clicker about this, and he asked it a question: how long would we think it would take? I think it turned out to be greater than 10 seconds. I don't remember, but we took this magnet and we passed it through this aluminum conductor, and we saw that it took quite a while for it to pass through. So what was taking place in this demo was Lenz's law. So as the magnet was passing through the conductor, it creates a current and a magnetic field. And that changing magnetic field will create a magnetic flux that opposes the movement of this magnet. So as the magnet passes through here, it creates an electromotive force, EMF, that opposes the movement of our magnet. So that is our negative right here. And so these variables have a direct relationship with our EMF. Increasing them will increase our EMF, while increasing our time will decrease our EMF, which is shown in this demonstration at the beginning by producing a magnetic flux in this with this circuit right here on the left. It will induce an EMF here on the right. So that's my explanation of Faraday's law.